Good morning or evening or wherever it is where you are, wherever you're happening to watch this movie. Anyway, I've been requested to do a playlist on probability, and I think that's an excellent idea, so I will start doing a playlist on probability. So let's do a playlist on probability. Probability. So a good place to start, probability. I don't do videos on spelling. Probability. So what is it? And I think all of us have kind of a sense of it, very informally. And as far as I can tell, there actually isn't a formal definition of what a probability is. There are kind of several almost formal competing definitions. So just in our everyday life, if the weatherman says there's a 50% chance of rain, the next day, he's essentially giving a probability. He's saying that, well, there's a couple of ways that you could interpret the 50% probability. It could be that if 100% was that he is sure there's rain tomorrow, and 0% is that he is not sure that there's rain tomorrow, that 50% kind of means, well, he's kind of neutral between those two possibilities. So one definition could be how strongly you believe. How strongly you believe, and this is actually there's a whole school of probability where they view probability like this, and this is called the Bayesians, and we'll go into that more. And actually, when we do easy problems, all of these things kind of are the same thing, but later on we'll see what the difference is. Another way of interpreting this, and this is kind of the frequentist school of thought, is if I were to have the data or if the weatherman had this data that he has right now, as far as where the clouds are and what the barometer reads and where the moon is and all of the data, given all of the data that he has, when he has that same exact data 100 times, 50 times or 50% of those times there will be rain. So you can almost view it as given the data he has, if you had that data 100 times, or if you were able to run this experiment 100 times, although that's very unlikely that you would have that exact same number of data points, whether Mars is in the right place and the sun is flaring and all, it's very unlikely you have those exact same the butterfly effect. One butterfly can affect the wind patterns across the ocean. So it's very unlikely that you could perform that experiment 100 times. But what the weatherman could be saying is, well, if I did have data identical to this 100 times, 50 of those times, or 50% of the time, we would have rain the next day. So that's the 50% of experiments. 50% of experiments with same, I guess you could say, measurable initial conditions. I'm kind of doing this on the fly, so don't take this as gospel, but I think it'll give you the sense. With same initial conditions would result in rain. And they're almost the same thing, but we'll see later that, this frequentist, I tend to view the world kind of like this, but there are a lot of circumstances where it's hard to say that you could perform that same exact experiment over again. For example, if someone said in 2003 there's a 50% chance or there's an 80% chance that Saddam Hussein has weapons of mass destruction, that I think and that would be a probability. You'd have these CIA analysts who aren't being influenced by their bosses saying, hey, after all the data we see, we can't be sure, but we think there's an 80% chance. And that's what they would be in this camp, right? Because you really couldn't perform that experiment 100 times. There haven't been 100 times or 1,000 times or a large number of times where you had that exact same set of circumstances where you had a guy with a big mustache in the Middle East kind of giving the runaround for weapons inspectors. Anyway, so let's move on. I think this is very subtle, but it gives you the difference between these two things. It's quite subtle, but I think it gives you a nice framework for what probability is. So let's just do a little bit of notation. And actually, I actually looked it up on Wikipedia, and they had one definition. Maybe it wasn't Wikipedia; it was maybe another website. And actually, I think you do see this definition a lot, where they say, the probability, and sometimes it's written as probability of A. Sometimes it's just written as P of A. So the probability of A occurring is equal to the number of events, or the events in which A is true over total number of events. And this, for the most part, can be a good definition, but I'll show you one place where I think it's a little bit more squirmy. So if I told you that, I'm going to flip a coin, and actually even better, let's roll a dice, and let's say I say the probability. I'm going straight to more difficult things. So let's say the probability of an even number. Well, let's use this definition that they gave. Well, what's the probability that this event is true? Well, let's see. What are all the numbers I could get? I could get a 1, 2, 3, 4, 5, 6. This is just a normal die. It's not one of those Dungeons and Dragons dice. So what are the number of events where we get an even number, where this is true, where even is true? Let's see. 2, 4, 6. Those are all the situations where we get even is true. So there are 3 where even is true. And then what is the total number of events? Well, we could get one of 6 numbers, so there's 6 total, and that equals 1/2. And that also equals 50%, right? We know how to convert fractions to percentages. And this is right. This is completely right. But the only time where you can really apply this, and in most of what you'll do in school and things, you can apply this. But this assumes that all of the events are equally likely to occur, right? You could have had a dice or die, I forget how to say the plural, or the singular. You could have that situation where maybe, the 6-sided is weighted a little bit more, someone sanded it down, so it's more likely to have a 3 or something. And in that case, you wouldn't be able to use this definition. So I'm going to modify this definition, although I don't know if it's traditionally modified. This is one possible. Events in which A is true divided by, well, let's say equally probable events in which A is true divided by equally probable total events. So in order for this to hold true, each of these 6 circumstances have to have an exact equal chance of occurring. And we're going to do, maybe in this video, actually probably not in this, I only have 3 minutes left, but in this series I'll show you situations where, we'll have an unfair dice or die, or we'll have a set of circumstances where each of the total number of events, they're not equally probable. So that's why I want you to become a little bit wary of this situation. So with that said, let's do a couple of probability problems that maybe give you a little bit more intuition for what's going on here in the world of probability. So if I'm flipping a dice and I said, well, what's the probability of heads? That's pretty easy, and we could use that definition, and it's a completely fair dice. We could use that definition to say, well, what are the total number of events? Well, I could get heads or tails, right? So there's 2 total events. And the probability of getting heads, that's one of the events. So there's a 1/2 probability. The way I like to think of it, so we don't have to use that previous definition, is if I were to conduct this experiment 100 times, what percentage of those times am I likely to get heads? And then I would say, well, there's 50% of the time I would get heads. And the reason why, I could make a symmetry argument that it's just as likely to go on heads as it is to tails. There's no reason why I would expect 51 heads or 49 tails, although that could happen. But there's no reason I could expect it. Heads and tails are equally likely. They're just different words for different sides of a coin that's equally likely to fall on either side. Anyway. So what would be the likely? Let's say I'm going to now flip a coin twice. And it's the same coin. So I'm going to flip it, and I'm going to pick it up, and I'm going to flip it again. And so what's the probability that I get, I'll call it heads. So that's the probability that I get heads on the first flip, and then heads on the second flip. Well, look at it this way. If on the first flip, we already know that we have a 50% chance, or 1/2 chance on the first flip, right? So let's think of it of the frequentist philosophy. So if I were to do this 100 times, right? 50 of the times I would get heads, let's call that on the first flip, and then of course 50 of the times I would get tails on the first flip, right? Now we're at this state of the universe, and now we do the experiment over again, right? So of these 50 times, 50 times, what percentage of the times is the next flip going to be heads again? Well, we could say, it's going to be another 50% chance. Or you could say, well, it took us, in 50 tries, the first one was heads, And then of those 50, 50% are going to be heads again. So we get a 25%. I just multiplied these two numbers. And of course, to get heads and then tails would be 25% chance. Heads, 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 tails. And then this is tails, heads, tails, heads. I'm getting confused. Tail heads is 25%. And then tails, tails is 25%. Anyway, I'm rushing it because I'm 25 seconds over. I'll continue this in the next video.